sure I want to start the stream. Hey, everybody, welcome back. Or better yet, welcome me back. It's been so long. It's like a miniature spring break, isn't it? I thought I'd start class with a lighthearted look at data, just for the heck of it. So I got a couple pictures I want to show you. This is a graph from like 1948, where one dot equals 7 hogs. Each dot represents 5,000 hogs. So I'm showing you this not because it's sort of a multivariate thing, but not really. But I'm showing it because the funny parts of it are the comments below. And this is where I kind of want to get you into mocking things. Mock as many statistics as you can. All right, so this is from World Geography 1948. And it says here, untapped infinite hog supply in the ocean. Like that one. Each state is lined with an impenetrable wall of swine. We are trapped. Yeah. And we've lost Canada and Mexico to the hogs already. So, I like that. Like, if you see something like this, you want to pass along, like this. It's kind of a fun thing, but like if you can sort of mock your own like images and stuff, it's a good way of having I don't know, keeping it lighthearted a little bit. I try to keep myself not too seriously, and believe me, there's plenty of things for me to mock on me. But if you find things like this, please, you know, let's share this. Or better yet, as you go on through your grad career, if you start reading other people's papers and have comments like this, please post it somewhere. I think I found this on Reddit, so it'd be kind of funny. I also found this a while ago. This is from Halloween. Let me see if I can pull these up real quick here. Maybe. There we go. Scary jack-o'-lanterns. That one, or this one right here. Inferring causation from correlation. So if you have a chance to have any humor with statistics, I think it's good, right? I don't know. For whatever reason, that hog one, though, just makes me laugh. The impenetrable wall of swine.
Have you seen that? There's that one website that'll take series of correlations.
Oh, yeah.
Put them together. Like, one of them was like Nicholas Cage videos, which is similar thing. There's this like perfect correlation.
Yeah, I did. I think I've seen. That was something that hit Facebook like a while ago, I think. Yeah, it's pretty cool. So anyway, if you have any of those and you want to share with me, please send them my way, you know, just for fun. So, I feel like we've all grown apart so much in the last couple of weeks. And really, it's not you, it's me, but it's... I know, you've been here for me, and I've just turned my back on you. But I want to, first of all, thank you for your patience with me because, well, I had that travel thing and I was going to Miami. Turned out, don't tell anybody, I didn't actually make it to Miami, but everybody thinks I did. That ice storm happened, and there were people who were stuck on the runway, evidently, for like 12 hours or something like that at Kansas City. Well, I had the forethought to be like, hey, I'm just not going to go today on Tuesday. And then, so I rebooked my flight Wednesday morning, and sure enough, like at 9 p.m. on Tuesday, they'd already canceled that. I'm like, screw it, I'm not going anywhere. So one of the best things in the world that you can do is tell everybody you're gone, particularly someplace nice, Miami, and then just don't go. And it's amazing what you can get done when you do that. It's pretty awesome. So anyway, we would have had class on that Tuesday, but it was canceled, right? So we couldn't, and I didn't want to forget it. Then last week I was in Wichita, Kansas. There's a big pilot I'm part of with the state MTSS group, and we're collecting data in various schools in Wichita and Olathe. So that's where my head's been, and it's actually kind of neat because it connects to our homework, where you're trying to predict a categorical response. I'm predicting categorical atom responses. You'd think logit model, but I'm using actually a probit model. And predicting things that didn't exist. So it's kind of a fun thing. It fits all well together. And using Bayes, of course, too. So all stuff I coded, which was why I've been sort of in a different headspace lately. Because you know how my coding works after dealing with the homework system, right? So I wanted to just slowly ease back into class. So anyway, first of all, how many of you are terribly disappointed that we didn't do anything new in class? Alan? I'm sorry. Always a couple. No, I'm just kidding. I'll make it up to you Actually, no, go to my website. Go to the class from 2012 and be glad you're not those students. Lisa and I co-taught this class. We had like 9 homeworks and a take-home final. And it was a 4 hours of class week meeting in class. So if you go to that class, that's the most packed information we ever did. And I'm going through it now thinking, oh my goodness, how did we ever do this? It's a terrible idea. Anyway, the rest of you, I'm sorry, but there will be time. What this class is about is multivariate modeling, and I'm going to get there. We're actually about to start that. But I want to use this class period to refocus us and try to talk about where I think the plans for the rest of the semester are going to go so that we can have a great time doing multivariate statistics. And then we'll also use the time to talk about homework, because that's still due next week. But because I'm in a giving mood again, let's start with the rest of the week. I've dropped yet another homework from your list. All right? You're welcome. All right? So how many of you are terribly disappointed? Always one. Always one. Justin, is it? Sorry. Yeah. Oh, my goodness. Sorry. Always one. Oh, no, just kidding. I did that because just the alignment of where class is going to land and what I can reasonably do. It's hard to prep the class like a week ahead of time on the online videos for me. And so I'm trying to juggle all that plus other responsibilities. And so I'm trying to be more realistic in the schedule rather than optimistic. And so that's what we're doing. I dropped the last homework, which was on multiple imputation. We'll put a Bayesian homework in there. So I think that's cool because many of you probably won't have the opportunity to take a Bayes class, although Billy Skrupski teaches one. I'm teaching one in the fall, actually, too. But this will hopefully give you at least a taste of it to see how it works. But this is helping us stay much more cohesive because the second half of the class becomes this sort of mismatched set of topics in multivariate that are could be entire classes. So we've sort of dropped a few of those. Let me go over what else I have here. I have next week. That's right. Today's the 6th. Next week, somewhere between now and then, I'll have lectures on matrix algebra and multivariate normal, which nobody wants to talk about usually. But multivariate normal is our first multivariate distribution. So we're getting to where we need to have multivariate statistics. Matrix algebra is what you need to be able to do the multivariate normal to see what it looks like without going completely crazy. But we're only going to do little bits of matrix algebra. I'm doing both of those to introduce what comes after spring break, which is the multivariate linear models. What happens when you have more than one outcome in your analysis? We're going to start with normal variables, and then we'll switch over maybe to something where we have some that are not normal. In fact, that might be the Bayesian homework. Right? So that's where we're going to start with. The next homework will be something about multivariate models with maximum likelihood, and we're going to start that starting on the 27th. The reason why I'm doing that is because these multivariate models, when they come at you, there's 2 different camps of people in the world, and there's probably lots more than that, but 2 large groups of people in the way they do multivariate statistics. And one is, actually there are 3. One is the people who should never do it ever like that again, and we don't want to talk about them. They're using stuff that we did in the 1930s. We don't want to do that. Not that the 1930s was bad, but just it doesn't fit data usually pretty well. Then there's the group of people who come about multivariate models thinking about them kind of like you would with a factor analysis or a structural equation model. And what that gives is a real nice direct combination of predictors to dependent variables, right? There's a package in R named Levon. Ahmed is very familiar with. Ji-Hong is as well. I'm trying to think, was anyone else in my SEM class last fall? We use that for my SEM class. It makes it pretty straightforward because you say you've got, just like you have in your model now, you have an outcome, you put some type of tilde, you put a series of predictors. Makes sense, right? So I like that because it introduces you to the idea of what happens with the multivariate statistics. However, it has some limitations. First being, when we estimate it with smaller sample sizes, we get biased variances, which is bad, right? So the second is that gets us to that next set of models, which are mixed models. So path analysis would fall under that structural equation model version. Mixed models would sort of be the other big heading. You see a lot of people who are in statistics using mixed models. They show up in all sorts of forms, but there's the problem with it is it's sort of an indirect way that we access multiple dependent variables. We trick the software into thinking there's only one. And the way we trick it is with a series of dummy-coded indicators of variables and interactions. So it's a lot more complicated, although it's the same model. So my homework 4 and my homework 5 are going to be basically the same data set, analyzing pretty much the same model with 2 different versions of software. Because why you'd want to use mixed models is that they're kind of the standard that we use, this estimator for it gives you unbiased variances. And it's what we use when we get into multi-level models. It's what we use when we get into a lot of different models that are out there. Then what we'll do is I'll get into this repeated measures lecture is sort of so you can communicate with your advisor if you're doing any repeated measure studies, because they likely have learned it in the methods that were the 1930s. And so you want to be able to translate and tell them, yes, I'm doing the same thing, it's just better, and here's why. And then we'll get into Bayesian statistics. Bayesian statistics will be fun. We'll do things the same type of model again. So I'm thinking I'll do, the last homework will be a very similar multivariate model. It'll be in Bayes land though, so you'll be able to estimate it in Bayes. But I'll make it so that one of the variables, there'll be multiple variables and they'll have different distributions and whatnot. So we'll take what you did in homework 3 and mix it with the other ones. Cool? Cool. So you're still getting value out of class, I hope. Content. You know what an interaction is? Sick of them, yeah? No. Getting more confident in them? Cool. So yeah, I'm dropping several sections from class. The bootstrapping lecture I don't even have. I was going to make that brand new, so that might go by the wayside. I may have my dates wrong here. I noticed that earlier. Hang on a second here. May. The last class, actually, I have my date. I'm getting off on my dates. The last class should be May 1st, right? I think so. Yeah. All right. Well, we'll talk to you about it when we get there. Okay. But the others, I do have older lectures on principal components and exploratory factor analysis that I'll put up. And I have older lectures on clustering and classification. But again, each of those is sort of like an entry point to a whole class of stuff that you want. But I'll give you all the resources I have on those, and then hopefully you can relive the glory of me teaching former classes and how bad the jokes were then. See if there's any change, things like that. All right, have I bored you to death yet? Questions on plan? No, and all of this, of course, is subject to change because who knows what's going to happen, right? I could be sick. I could get paid $2 billion to go away. I mean, I love all of you. Don't get me wrong, but no, I'm just kidding. I anticipate I'd like to finish the semester. I'd like you to get something out of this class. Okay. Always with this, though, if there's something that I'm not covering that you'd like more information on, send me an email, and I'm happy to help find some resources to point in the right direction with it as well. Okay. Other questions? Comments? Okay. Let's go back to generalized models. Generalized linear models, which is where we left off before. Those lectures were intense, weren't they? All sorts of like abstract, very few concrete things. If you were to summarize what a generalized linear model is, do you think you might be able to, who wants to take a stab at what that is? Just smallest bullet points. What does generalized mean? If your advisor asks you, what are you learning about? You said generalized linear models, and you're like, okay. There you go. It's for data where you don't just have normal outcomes. Boom. Linear model means ANOVA regression, right? So it's ANOVA regression on things that aren't normal. And how does that work? Do we transform our data? Huh? Who says yes? Good. No, we don't transform our data. We transform our model, right? You may be thinking, yeah, I learned how to transform data. Just unlearn it as much as you can. So the generalized linear models are really trying to take the good things about linear regression and ANOVA, if there is such a thing, and put them onto data that don't have a continuous space, where the parameters don't can take any number, right? So for instance, in your homework, you have an outcome that's a 0 or a 1. It's categorical, binary, dichotomous. Those are synonyms for what we have. And we know that with a general linear model, with a regression ANOVA type model, it's trying to predict the mean of the outcome. But the mean of your outcome when you have a 0 or 1 variable can only be between 0 and 1. So we have to do something to make it work, and that's where the complication comes in. We have to use some type of what's called a link function, right? The link function takes the mean and converts it to the space of the full real number line from negative infinity to positive infinity, and we're effectively predicting the mean of that, or the link transformed mean, right? So in your homework, the link function is this logit. You like logit? Does that sound terrible? Anyone would call it logit? Log it? No. I don't know. I've heard some of my friends, some of my former students who were up in Minneapolis, they call it a logit. But I'm not there yet. Hang on, let me just try to get back to my notes. It's like I've never done this before. Excuse me. Okay, so yeah, if you have a proportion, right, for a P, I guess I said, oh heck, I'll just do this. The outcome for a person equals 1. We're going to call that pi or something like that. That's a proportion, right? That's the probability. That's the mean, right? We'd sometimes call this is synonymous with y bar overall, which is also equal to the expectation of y. Right? There's all those things are the same. Am I doing something wrong? No. Okay. Sorry. No worries. I'm not trying to pry. I was like, the look on your face was there's something off with me, and I'm like, uh-oh, did I say something bad? Yeah, I know. I'm with you too. No, actually, the whole thing. Yeah, here. I'm with you. Actually, that's good because I'm feeling that same thing too, and I do this for a career. Right? So if I'm doing this for a career, and I'm like, where were we? Oh yeah, what? I'm with you. And I apologize for, I'm not trying to call you out, Miriam. I was more, usually if there's something funny, I want to be part of it. Like if it's about me, I would like to be part of it at least, all right? So you can make fun of me. It's totally cool. In fact, I may give you extra credit, all right? You know I give that away like candy, right? Actually, I give that away more than I give away candy. So what I'm trying to say is this. If you have a bunch of data, a bunch of zeros and ones, right? This is y. Right, and this is person 1, person 2. Right, the mean of y. Oh no, don't do that, Templin. X. I can't even draw now. Y bar. Right, that thing has to be somewhere in between 0 and 1. Right. Right. That's the math notation for it. Somewhere between 0 and 1. And again, we sometimes call this the expectation of y. You may see this in the notation. The generalized linear models are so dense notation-wise. And so I'm just trying to detangle it a little bit. So hang in there. But yeah, if you feel like, wait a minute, what's that word? Just say something, please. I want to try to tag that with better information. So can I just call it y bar instead of pi? Does that work better? So we're thinking of the mean of y. Okay, what really this mean happens to be, because it's the sum of y over n across all the people, right? This thing. Because of that, this really represents the proportion of people where y equals 1, right? That's really what that's trying to tell you, right? So what this whole analysis model tries to do is say, okay, this thing's between 0 and 1, but there are a bunch of other ways that we can take what the mean is and convert it to other numbers that we can predict instead, right? And one of those ways is to go and say, hey, I want to take one of the things you see a lot is the odds, right? The odds of an event occurring. Odds. So I'm writing at an angle here. Maybe I'll just tilt my iPad differently. The odds that y of y equal 1. Right? It's usually the odds of something happening. Odds. Let's say what do you want y to be here? Let's put some context to it. Can you think of a binary variable in your life? Varies by person. True, although if we try to predict that, probably not a good outcome. But no, sorry, I just say that because we're going to get to mediation in the middle of class, and sometimes you'll see sex as a mediator. Like, what predicts biological sex? But sorry, Sammy, but you... Get into college or not? Let's call it, yeah, admitted to college, right? It's about that time of year, or maybe not. It's been past that time. People are admitted or not, or whatnot, right? Y is admitted to college. There we go. Okay, the odds that someone's admitted to college, the odds of that would be that probability, or better yet, just keep it mean, keep it real on the mean here. Y bar over 1 minus y bar. Right? So that's the probability for the event happening over 1 minus the probability the event happens. And odds are crazy because I have a hard time thinking in odds. But if you're in the biostat world, Ahmed, when you work, when you're GRA, do you have odds ratios and things a lot? So Ahmed is in a medical area for his GRA right now. And so for those of you who are in health sciences or otherwise, you may hear about that. But I don't come out from the health sciences, and so I don't think in odds very much. But odds, the way I like to think of them is if the mean was 0.5, if equal number of people got into college than didn't, the odds of going to that would be 0.5 over 1 minus 0.5, which would be 0.5 over 0.5, or 1, right? So that's kind of like saying 1 to 1. It's a 1 to 1 chance that someone's in there. That's where I think of odds. Who gambles? I don't gamble anymore, but I used to. Who's been to? Yeah, there you go. So not all of you do, but maybe you heard, well, the odds of this happening, or the odds of this horse winning this horse race or whatever else is 3 to 1, right? Bless you. That would represent a situation where this odds ratio would be a 3 instead of a 1, right? And how would that happen? Well, if the probability were to be 0.75 over 1 minus 0.75 equals 0.75 over 0.25, which equals 3, right? So you'd say whenever the odds, or whenever the mean is bigger than 0.5, you have odds that are greater than 1, that the event's more likely to happen than not. And the flip happens whenever... let's say, well, let's take the opposite. If admitted to college, if only 25% of our students were admitted to college, KU's budget would get cut significantly. We depend on that sweet, sweet student money, student loan debt. Sorry, it's terrible. Like, college is terrible these days, and I propagate it. I know, but 0.25 is here. So you can see how this works instead. 0.25 over 1 minus 0.25 is really 0.25 over 0.75, or 1/3, right? So that's how you'd see odds. So anything between 0 and 1 says the event is less likely to happen, or another way of putting it, the mean is less than 0.5, right? So because there's two outcomes, when the mean's bigger than 0.5, one outcome is favored, the other, the odds are bigger than 1. Yeah, Alan.
So that'd be 1 to 3?
That would be, that's right, 1 to 3. It's hard to say. The odds are 0.33, but yeah, it's exactly right. It's 1 to 3 odds, I guess. And this is why I have such a hard time describing them. Maybe Ahmed, am I doing that all right? Okay. Yeah, I don't think in these terms. I don't like them very well. I do not like, I'm trying to think of, my son's now into green eggs and ham. Trying to think about that with odds. I do not like green odds. No, I don't know what else would go with odds. But, so odds has a problem because the odds range from 0 up to positive infinity, right? So we don't have that full space of numbers if we were trying to predict the mean of an outcome, because we've got that lower range of 0. right? So what we typically do is take the log of the odds, right? And it's usually the natural log of y equals 1, like that. And so when we take the log of this value, now the odds, now this log value, what we can see is if we go with this number line from positive infinity, or negative infinity up to positive infinity, with 0 in the middle, this 0 right here represents a probability or a y bar of 0.5. So if I put y bar over here, right, so this is a 1, this is a 0. So anything greater than 0.5 represents a log odds or a logit. It's positive. And everything less than 0.5 gives you a log odds that's negative. And the nice thing is, I talked about this a little bit on the recordings, but again, this is a tough lecture to even teach, let alone listen to. The odds are what I call reflective about 0. Right? So in probability, when two probabilities sum to 1, they're called complementary. Have you heard that term before? So 0.75 plus 0.25 are complementary of each other. Right? So what you can see is the probability of 0.75, let's see here. I should just know, it's log of 3. We knew that before. Log of 3 is 1.09. So right here, 1.098, of course, 1.0986, because I rounded, you know, if I were to round up to 1.1 right about. So now the complementary probability of 0.75 is 0.25, right? And so we know, because this is sort of reflective about 0 for it, the odds for the 0.25 is that same number, but now with a negative in front of it. 1.0986. So that's one of the nice things about it, is that however big the odds ratio or the log odds gets positive, you know that what's left over in probability is that number being negative, right? So it sort of gives you a balance, maybe. Is this helping at all put things into context? Or at least reframe? Juhi. Yeah, this line right here is probability. The second line down at the bottom. And this is the logit. I'll just call that logit right here. All right. So does this help at all, or is this just repeating? I know it's been a while since I gave these lectures, so I'm just trying to bring us back. If this is a repeat, I'm sorry. I'm going to start making it crazy for you, though. Not too crazy, but I just want to get the process down a little bit, right? So the key to this, though, the key to any of these generalized little linear models is you have this shortened range that y bar can be on, right here. And if we take what the generalized linear model, what the link function is doing is taking a function of y bar and expanding it from negative infinity to positive infinity. That's where the bounds go. That's all it's doing. Right, it's basically saying, hey, your range is here. We're going to switch it to this. When we have it from that full number line, we're going to treat it just like we would treat any other regression or ANOVA. Right? We're going to predict it. We're going to put main effects in. We're going to put interactions in. We're going to talk about simple main effects and conditional main effects and all the things that complicate things. But it's just now, instead of talking about it with respect to the data, we're talking about it with respect to the log odds or whatever that function is. And there are lots of functions that can do this. So what I was just talking about in my pilot study with the state, you remember, did any of you take stat classes where you had to look up a table in the back of the book? Do they still have those? All right, what table did you look up in the back? Sorry, I haven't looked at a table in years because I learned Excel gives me all the numbers in the table and more accurate. The Z to what? The Z score? The Z and F, right? So did you, do you remember the cumulative distribution of, what a cumulative distribution is? So this is one of the ones that shows up in there. If we have a normal distribution, let's call this normal 0, 1. So the mean is 0. Standard deviation is 1. This is the PDF. So we know the area under that curve was 1 that we talked about. The cumulative distribution takes some spot, let's say this one right here, put x right there, and it says, what's the area to the left of x? Basically, what is the probability that you observe x or below it from this distribution? Have you seen that? Usually there's a z to like inverse, sometimes they call this inverse z. Have you seen that before? And so if you were to look at this distribution, sometimes what we call this function oftentimes uses the Greek letter phi, or phi if you're not from this country, phi of x, right? Now you call it phi elsewhere overseas, right? P-H-I, that, right? Okay, but here in the United States, I believe we call that phi, if I'm not mistaken. Or am I just crazy? No? They call it phi, or? Oh, well, phi then, phi. I like that. Phi, phi, fo, fum. Yeah. All right, I'm all screwed up. This thing is really telling you the area under that curve. That's what this is. It's a function of x. It's an ugly function, right? We know, we talked about the people in that room doing calculus, right? To do it, you have to integrate below, the area under the curve comes from something called integration. We're not going to do that. I don't want to do it. Just remember phi does that, and there's some function out there that will give it to you, right? But basically, you plug in x, and it gives you area. Right? So if I were to plot x down here, right, this is x over here, and I were to plot phi of x, it would look, here's 0.5, here's 1, here's 0. This curve would look something like this, right? Like an S-shaped curve and sigmoid function, sometimes called an ogive. And right at x being 0 here, we know that because it's a normal distribution, it's symmetric about 0 when symmetric about its mean. We know half the density is below 0 and half is above 0, right? So this would really represent the 0.5 function. Where am I going with this? X can go from negative infinity to positive infinity, being normal. But the cumulative distribution of x can only go from 0 to 1. So now, if you think about it, if you think really twisted, we could actually take, if we knew what the probability is, like 0.75 here, we could go and figure out the x that goes with it. And now we have a link function. There you have it, right? So it's like now, this fits the criteria that we need, right? We have something on one side of the function that goes from 0 to 1. We have something on the other side of the function that's unbounded, negative infinity to infinity. We can use it. So it's going to transform our data. What we're going to say, actually transform the mean. What we're going to say is that this is what we call the, sometimes this is called, if the other one was logit, this is sometimes called probit, a probit link. I know. Where'd that come from, right? But basically we take the inverse of x, right? If x is between negative infinity and infinity, what this function gives us is a number between 0 and, actually, pardon me. Phi of x gives us a probability. Yeah, phi inverse of x gives us this number between negative infinity and infinity. See where we're going with this? Sort of just conceptual. I don't want to do anything else yet, just conceptual. Questions? Why do you need to use this? That's probably what you're thinking, right? Well, there's a whole bunch of these when it comes to binary data. Like Google it. Here, I'll just do Wikipedia because I like Wikipedia. Nope, didn't see it. Never mind. Anyway, there's a whole bunch of them. Just take my word for it. Or better yet, don't trust me. I don't want to be trusted. I can't be trusted with data. Go back. Wow. Okay. In SAS, there's a procedure called Jin Mod. Sounds great. And sure enough, under the model statement, you should be able to see the links right here. There's all sorts of these. Log, logit, probit, cloglog. It's one of my favorite. It's complementary log, cumulative probit, complementary logit, or cumulative logit, cumulative complementary log. All sorts of things, but they all work the same way. In goes a number between 0 and 1. Out comes a number that gives you all the number line. So just to keep generalizing it a little bit more, let's imagine we have y, and we're back in the normal linear regression land, right? Where we were before we got to this crazy generalized course. This blew my mind when I saw it. It may not blow your mind. It might blow it in a bad way, like, just stop talking, right? But I was like, get out. You could do that too. You could do this too. Let's imagine we have a simple linear regression model where x can be either a 0 or a 1. So it's a simple two-group ANOVA, right? And we know that error follows a normal distribution with a mean of 0 and a variance sigma squared error. And what we see is because for each, this should have person subscript here, for each person, y, we have this same assumption that error is one value. We call this homoscedastic. We have this assumption of homoscedasticity. Sorry, I say that because I have to keep it rolling off the tongue. Constant variance, regardless. Wow, that's awesome. No, maybe that's not awesome. What are you doing? Didn't even know that was possible. No, I don't want to see that. Anyway. All right, forget it. You're going to see my iPad. I don't even know what I did with that. Anyway, there's like not even an option for it. All right, well, we'll figure this out. Okay, there you go. How cute. Break up this complicated lecture. So, yeah, you have homogeneity of variances, constant variance. Everybody in either group has the same variance. But what if that's not the case? Did you ever learn in the previous class what to do if you have violated your assumption of homogeneity of variance or constant variance? Anybody? Huh? No one wants to talk. Well, if you knew generalized linear models, what's that? Oh, there you go. Yeah, there's a test for it. Yeah, Levine's test. Very good. Yes. There you go. A Bonferroni would be if you have multiple comparisons. At least the Bonferroni I'm thinking. Bonferroni is probably a prolific writer, but the Bonferroni test I'm talking about is if you have multiple comparisons and you're worried about having an overall type 1 error rate or type 1 error rate high, you cut the critical p-value down by the number of comparisons you have. So it's not exactly Bonferroni because in the Bonferroni case you'd be looking at multiple betas or multiple hypothesis tests. But it's on the right track though. So yeah, there's tests for homogeneity of variance, but what do you do afterwards? When I was learning statistics, I was, oh yeah, use non-parametric statistics. Yeah, that's going to help, right? Here's what you can do. Bless you. There's nothing that stops you from modeling the variance simultaneous to modeling the mean. You could create a model for the variance. What do you think about that? What? This is cool, right? Here's where it gets really cool, for me at least. Okay? Because sigma squared E is over here. Maybe if we put a model for the variance, we can say each person might have their own variance. We're going to try to predict what the variance, what residual variance happens to be for person. What is the range of variance? What values can it take in a number line, on the number line? 0 is the lower bound. Positive infinity, right? So it can go between 0 to positive infinity. Wait, we've seen this before. The odds could go from 0 to positive infinity, right? And how do we fix the odds to have a bigger range? We took the natural log. What we're going to do, we could do the same thing. We could say natural log of variance is equal to, and now I'm running out of parameters and coefficients, but let's just imagine maybe it's related to which group you're in. I'll put gammas in like that. Those are gammas, right? Lowercase template written. I can say gamma. There's nothing stopping me from doing that. I can actually model both the mean and the variance simultaneously. And not only that, remember maximum likelihood? In goes function, or you have a function. It's got something for the mean, something for the variance. Out comes height. It still fits in that framework. Because you could fit in, once you know each of these parameters, you could form mean, you can form variance, you have data, you can make it work. Pretty wicked, huh? So, yeah, you could model the variance on top of modeling the mean. In fact, if you want to see where I did that, I don't think I'm going to be able to do this year, which is sad to me. Last year about this time, I created a multivariate model to predict the scores of the NCAA bracket tournament on the website. And see if I can get there. These are the probabilities that came from it. Let me see. Not too well. I mean, it was of all the games in the tournament where I predicted just before that game, I did about 80%. But that's sort of a. I mean,
it's a big deal. He actually, the news wanted to interview. He's just being.
No. Yeah, I was on the news, but I was really big in.
He was on the news.
Like the worst one was the well, I mean, this is last year, like right on the heels of like the bad news about Josh Jackson and all that was going on. And I felt like KU News was like, let's get some good news out, right? And so I was like, I'll take one for the team. They're like, you might be interviewed. And so then I was on like the morning show, and like Channel 9 had a and they came like, yeah, we'll meet you in your office at like 6 in the morning. And I was here from 6 till 9 doing some type of thing every like hour. I think it was, maybe it was every half hour. I don't remember. Anyway, yeah, it was. Anyway, news, blah, blah. Anyway, what I'm looking at here, is this. If you have, I called it consistency, basically of the error, each team would have a little more or less error or consistency, but that was the log of the variance. So I took a model where I predicted each team's score against each other team's score. Let's see if I can find the model here. Nope, probably not. And then I just modeled the variance as a function of team as well. And I was able to determine, this is last year's data, the bigger effects for team or the smaller effect, basically how consistent a team was in addition to like where their scoring average might be. So there's ways that you can do this. And actually I use Bayes for this because to build, when we get to the Bayes part of it, all this likelihood stuff I'm talking about really becomes relevant because you sort of have to pick out the distribution and put the different spots, different variables in the spots. And you could do this too, like the algorithm, you have access to all of it. But on that note, I actually also created whether or not a team played close to its opponent or not. I took the correlation and did this. Now, again, just to get you the picture of generalized linear models, when we get to multivariate models, we end up having not just means and variances, we have covariances. And we saw before that covariances can turn into correlations, right? I decided I wanted to model the correlation as well. So, correlation, I'll just put rho down here. And put it with respect to a pair of observations. This would be like A and B. This thing has a range of -1 to 1. Actually, I should put inclusive here. All right, -1 to 1. What do I do with that? Well, here's the process I thought of. Can you think of the process? What would you do if I'm like, hey, model correlation? Do a linear model for it. First thing you got to think about is, all right, what's its range? -1 to 1. I want to make that -infinity to infinity. Do I know a function that does that? My answer was, no. Huh. So I went to Wikipedia. Kid you not, right? And I remember I just started looking around like where functions might be, and I come across the inverse hyperbolic tangent. I kid you not. There is a function called the inverse hyperbolic tangent. So those of you who didn't go through trigonometry, or those of you who did like me, I did that in college in my path to get back to learning math. I was in remedial math to begin with. I don't know what that does. I don't know how it works. I do know that it takes a number from -1 to 1 and converts it to a number that's -infinity to infinity. And sure enough, with that, I modeled it with, oh my goodness, I'm running out of characters here. I'll use etas. Eta 0 plus eta 1 like x, something like that. And it works the same way. And I can do it all simultaneously within the same model. So this is part of the reason why I'm doing generalized linear models for you, is because even if you have a single outcome, you might be making multiple predictions about parts of the distribution of that outcome. And with respect to this, like predicting variance right here, with respect to this thing, this model no longer assumes you have constant variance. In fact, it's saying, I can actually test to see whether the variance is constant. That's what this parameter right here is. If that's 0, it's constant. Everybody has the intercepted variance for their constant value. But even if it's not constant, it doesn't hurt me because it's included in the analysis. It's there. Now, yes, I could get the wrong model for the variance, and just like the wrong model for the mean gives you the wrong estimates, there's all sorts of ways that could be wrong. But I feel like this gives you a little bit more precision in what you're doing for the model. Did that blow your mind at least a little bit? Yeah. Ryan. We gotta do what? The interactions are often on the, yes, you can. Sorry, as a predictor. Absolutely you can. If you have more than one, if you have an x, oh my goodness, I did this wrong. This should be x over here. This shouldn't be beta. X, if you have an x, like the x and z example I commonly give in all of my slides, you can do that as well. The other part to this that I've been trying to do, part of my research with this is I've been working on models where they're measurement models. They're like factor analysis, where you're trying to measure some trait about a person, but it's not just the mean that indicates the trait, it's also the level of variance. What motivates me on this is I had some data from a gambling study I was part of. I know I've told you, Ryan, this story. Let me share this with you. It gives me a chance to tell you all this. Ahmed's heard this. Jihang's heard this. I was in grad school, part of a lab. We got a grant to go collect gamblers from a gambling casino boat in Illinois. As part of our collection protocol, one of us had to sit at a roulette table for long enough to be able to observe who's been there long enough, and then whenever they got up to have one of the people in the back kind of intercept them and say, hey, would you like to earn some money? Come to the back of the casino. The casino was totally in on it. We had their security tapes, all the stuff, right? We gambled with grant money to be that person. So yes, that's like my favorite part of it. I think the professor who did that grant just wanted to give us all stories to tell the rest of our career. Anyway, with that though, pretty much it doesn't matter, how you ask a question. If a person's not a gambler, they're going to say the lowest category of response to almost everything, right? So if you're not a gambler, and so I ask you, do you think about gambling a lot? You're going to say, no. Or I'm going to say, or I change the format. I'm like, well, wait, yes and no might be too strong. Let me do a Likert scale. How often, or, let me see how much you agree with the statement. I frequently think about gambling. You're going to be like, I totally disagree with that, right? No. Well, I was trying to think, is there a way that you can use that information to help better measure what a person's level of gambling trait happens to be? So I've been trying to play with a model for that for a while. I have it. I have a question. Yeah.
I'm wondering what's the relationship between the use generalized linear model to predict the variance with random effect?
Well, in the random effect model, see, I'm doing everything with a fixed effect right here. The random effect would, if I were to put, so often a random effects model, Jihang is asking about random effect, a mixed model. We're going to get to that after spring break. Mixed models are random effects and fixed. But often we have multiple sources of variance in those. In this, I'm saying there's only one source of variance. Maybe just have single level data. And in a random effects model, even if we have multiple sources of variance, so perhaps in this case, we had this design, but it was nested within school, so now we had a school effect to worry about as well. We could take both of those variance components and do the same type of prediction as well. So anyway. So what I'm trying to tell you with this, why I'm trying to tie things in research, things in data to your understanding, not to overwhelm you, although I feel like I may be overwhelming you. If you're overwhelmed, I'm sorry. But let's get back down to underwhelmed, maybe. Anyway, if you're interested in learning more about some of these models, this one right here, often is called a location scale model, which is a weird way of putting it, but location means mean, scale means variance. So that's another way of doing it. Okay, back to the topic at hand, though. The picture of generalized linear model is always, you've got some type of parameter or some type of feature of the distribution you're using that causes all sorts of headaches because it doesn't range the full number line. And because of that, if you were to go and use some other type of linear regression with it, you'll quickly get predictions out of bounds, or you'll get things that don't make sense, but also you'll have bias in your standard errors, and you'll have all sorts of things that it's not a good fit, right, between the two. So that's why we're working on this in class here. So getting back to it, so specifically for us, we're doing the log odds, right? Let's go back to logit. So here. So again, y equals 1 means a person who was admitted to college, right? And let's imagine we have, so 0 means not that, right? Templin. I'm so sorry. I'm going to make you go away on the screen, but oh well. Can you all see, is this big enough to read now? All right. So admitted to college versus not. And let's take a predictor here. Who wants to name the predictor today? What's X? Anybody? What influences your person's ability to be admitted to college? What? SAT scores? GPA? I'll say GPA. Not that I hate the SAT. I sort of do, actually. Actually, you know what? I hate the GRE. Kid you not. As a person who studies psychometrics and a person who admits students to grad school, I never use it. So there you have it. What's that? So just, and I always fight with my colleagues on this. But my standard is always, one of the reasons, first of all, I question the validity of it. Same with the SAT. But second, plus there's a lot of reasons for this bias-wise and everything else. Although I know they study bias quite a bit with it, I still think there's more social issues than that. But also on top of that, I think just pragmatically speaking, you got to tell me each person's standard error of measurement when you give me their score. Because each person's score is not all scores have equal reliability on the GRE. So if you sit next to somebody and you both paid the same amount and you both got the same score, one of your scores might be more reliable than the next person next to you. How do you like that? Sorry. So just from let's just assume there's no bias, nothing wrong with it, perfectly valid. I still can't tell how reliable it is for two people. So yeah, that's still a problem. Okay, but let's just take GPA, right? Because that's also an indirect measure of what you've done in high school and whatever else. So what we're going to do is model the logit, that y equals 1. That's sometimes how I write it. And we're going to use a regression on it, beta 0 plus beta 1x. And we often have a person subscript for this, right? So now how do we interpret these parameters? Beta 0. In regression, we call that the intercept, or the predicted value for someone whose x is 0. So this is if we were doing just straight regression, this would be a person's predicted value of getting into college for a GPA of 0, unless I mean centered GPA or centered at some number. Like in my example, I guess I did GPA minus 3, right? So how about I just call this GPA 3, like I did in my example. GPA 3. So that means for a person who has a GPA of 3, the intercept represents what? Now, it's no longer the actual getting into college. It's not the dependent variable. It's now the logit of the probability that somebody gets admitted to college, right? So this is telling you essentially what their chances of getting into college are. It's just not in probability. It's in with respect to logits, right? And that's the weird thing about it. It directly, like to talk about this, you have to be in that academic club, right? Where everybody knows logits and you all speak the same language, and if someone joins the conversation, like if you're learning this, like in multivariate, like I used to be, and people start talking logits, you're like, what the heck, right? By the way, in grad school, I spent 3 years not knowing a darn thing in my program in quantitative psychology. 3. And I remember the fall semester of my 4th year going to one of our seminars, walking out with my friends, we'd always ask the same question. Did you get anything? Did you understand any of this? And finally, in year 4, at the beginning, I think I might have understood that. Right? So it takes us all a long time. So it's weird. So let's imagine this logit was 0. Right? Let's put some context to it. And let's imagine this one was a 1, just to give it some context, right? Right? So this value, the 0 represents the log odds that someone with a GPA of 3 gets admitted to college. But we can always back translate that to a probability, right? We can take E to beta 0 over 1 plus E beta 0. Now EXP really means 2.71 something or other. Euler's constant, something like that. EULER. You know that thing? Math. Again, I'm so terrible. Math is an acquired taste, right? So this is E to 0. I'll just put E to 0 over 1 plus E to 0. And anything raised to the 0th power becomes 1, which equals 1 over 1 plus 1, or 1/2. Or 0.5. So this says basically a person has a 50-50 chance of getting into college when their GPA is at 3. That's what's it saying, right? So if you sat there and went, what does a logit mean? You're probably like the rest of the people who you're writing for or talking to in the audience whenever you're doing a study. Right? So it always helps to translate logit to probability whenever you can. Right? Sometimes you can't. Particularly anything you're taking a difference of, like a difference in logits, harder to translate into probability because it's going to depend on where that difference is coming from, right? The difference in probability will change because it's a nonlinear conversion to go from logits to probability. When you're taking a predicted value, absolutely change it to logits. Provide some context. Is this helping at all? Okay. What if that beta 0 was, instead of 0, negative 1.10? Why do I say negative 1.10? Because I wrote that down way up here, right here. Negative 1.10 is right about what that is. So now that's telling you that for a person whose GPA is 0, or GPA of 3, right? So this term right here goes away. That their expected logit is 1.10, and so that means that their probability of going into college, get admitted to college, if we work our way through, would be 0.25, right? And we know it's going to be less than 0.5 because that logit value is less than 0, right? It's on the left-hand side, your left, my right, right? The left-hand side of the number line from 0. Now, similarly, this is why I like logits. What about if that was 1.10 instead of negative 1.10? Remember, now we've switched the signs, so we're now into the complementary probability. So that says a person whose expected logit of getting admitted to college is 1.10 turns out to be a probability of 0.75. Right? So the way it works is sort of there's an extra step between model and interpretation, and it's back convert to something that's understandable, right? If you can. How are we doing? Helpful a little bit? Maybe? How about we try to interpret this slope then? All right, so now GPA 3, we have a slope of 1. If this were regression, you'd nail this, right? You got this. For every 1 unit increase in GPA, or in this case, since GPA is on a 4-point scale in my head, I didn't define that ahead of time. I'm sorry for those of you who are used to a different scale, but let's say 4-point scale. One unit of GPA means 1 letter grade higher, right? So a GPA of 3 is a B, a GPA of 4 is an A, typically speaking, right? So for every 1 additional letter grade, a person's GPA goes up. the expected logit goes up by 1. Right? Now this is where it becomes a little bit harder to start talking about comparison, because what the probability happens to be depends on what the intercept is. We have to add the intercept to our analysis to make it make sense. And so if we said, let's take a GPA of 4. For a GPA of 4, GPA equals 4, which means GPA 3 equals 1, really. Right? So that means that if we keep 1.10 here, the expected logit would be 2.10. So that person's probability would be, excuse me. Sorry, I have no manners when it comes to putting the Apple Pencil. Nope, that's wrong. I didn't do that right. This should be E of that divided by 1 plus EXP of 2.10. That probability is now leads to probability of 0.89. Right? So now what you're saying is, okay, for a person whose GPA was 3, their probability was 0.75. A person whose GPA was 4, their probability is 0.89. That's what the model is telling you. And I found in my stat practice, makes me sound like a yogi or something like that, my yoga practice. So I like to think of it like yoga with statistics or something. Maybe not. I just ruined yoga for everybody. It's supposed to be calming and relaxing, and it is to me, though. Oh, look at those statistics. Anyway, what we're saying is that a 0.89 probability, it's easier to go and talk about ranges of predicted values with the model. So if ever is possible, kind of plugging in values and talking about what that means in probability sense helps. Right? The other thing that happens, though, because these probabilities shift depending on where the intercept happens to be, right? So if the intercept were to be 0, let's see if I can do that. The intercept being 0, so hang on here. This is when, this part right here is when beta 0 equals 1.1 and beta 1 equals 1, right? What about these probabilities when beta 0, heck, I'll just do negative 1.1 and beta 1 equals 1. Should we do that? Kind of show the same comparison. How do we convert, what is the probability for, this is GPA 4 equals 4, GPA equals 3, GPA equals 3, GPA equals 4, right? There we have our two GPAs, our two values. How would you go and form the predicted value for someone with a GPA of 4? Again, you go back to your betas, like we do with the linear regression. We take 1 beta 1 and, in this case, negative 1 for beta 0. So that gives us a logit of, was negative 1.1 plus 1 equals negative 0.1. So the probability would be, oh shoot, yeah, here we go. Probability. Love it. Oh yeah, cannot find the server. Hey, you just found it. Anybody want to help me here? Actually, forget it. You know what we're going to do? We're going to pull up our friend R. I wish I could talk to R like I do Siri. Okay, R. What's the inverse logit of negative 0.1? You want to try? What's the inverse logit of negative 0.1? Sorry, I did not get the question. You're useless, Siri.
After all I've done for you?
Yeah. All right, 0.475. 0.475. I'll go back. I'll write this on that one, reflector, 0.475, right? And the logit for someone whose GPA was 3 was just negative 1.1. So it gives us a probability of, back to R, it's smaller clearly. This is now 0.25, let's just say. So now, do you see what I'm talking about? The difference in probability changes as a function of where the predicted value is. Right, because this difference is 0.475. If I were to take the difference between these two, the difference would be 0.225, right? That's the difference between the GPA 4, GPA 3 when the intercept was negative 1.1. The difference between these numbers was 0.14. That was when the intercept was 1.1, right? So when we're comparing, we're starting to do comparisons, it sort of depends on the other values in the equation is what I'm getting to. But you get the basic sense of going predicted values in logits. Let's go back and put it in probability. Do you get that part at least? More or less. It's a little bit unnerving, but it is possible to do, even if Siri doesn't want to cooperate. What's my name?
You're Jonathan, but since we are friends, I get to call you Awesome.
Sorry, inside joke. You probably heard this before. My daughter in preschool, when she was learning about middle names, she's like, yeah, my middle name is Hazel. I'm like, yeah, well, my middle name is Awesome. And I kept saying this to her, and you know, I was living in Georgia. She was in Alabama. It turns out she tells all of her friends, my dad's middle name is Awesome. My dad's middle name is Awesome. So this became a thing when she was like 8 or 9. When she got to be 18, she was going to change her middle name to Awesome. But now, doesn't sound like that's going to happen. Adolescence is taking its toll. Anyway. Yeah, so I'm awesome. That's where I go with that. But no, I'm also overconfident. You can go with that one. Cocky. Okay, let's go back to this. So how many of you are kind of like, I hate logistic regression already? Yeah, it's okay. You can hate it. Hate is okay for statistics. You can hate certain statistics. Maybe yet let that be like, you know, it's not good to hate people or you know, I don't know, too many things, but you can hate statistics, right? Logistic regression's hard. It really is. It's not what you're used to. You have to go through it. Let's talk about homework then, shall we? Okay. Close that. Yeah, let's see if you find the server now. Okay, homework 3. You want to go over the whole homework assignment just from start to finish and start walking our way through it?
I guess.
You guess. Those of you who are advanced, I haven't looked at who's done what. I'm going to use Chrome though because it scales better, I think. Let's see here. Yep, there it goes. Templin. There we go. No, it doesn't scale the numbers well. Sorry for the small font. I'll just read it. You can follow along on yours, okay? Please note the following scenario is hypothetical only and is not derived from real empirical data. Please do not make any inferences about your own situation from my poor attempt at humor below. Okay? This is me just saying, yeah, quant skills help. Of course I'm going to say that. That's what I'm trying to sell you. That's why you're here. The data were collected as part of an interdisciplinary study conducted to examine the extent to which graduate school activities predict subsequent employment opportunities. Data were collected from a total of 500 graduate students from 10 different departments at Midwestern Red State University. I think that's where we had our mini golf example, right? Good place. Students reported their number of publications in print or in press, and the number of conference posters as evaluated in December for the first year they applied for jobs. Students also reported their amount of advanced quantitative training, which was then categorized into low, which is meeting your program requirements, medium, you took 1 or 2 additional classes, or high, took every quant class you could possibly take. Whether the student was offered a job in their first year on the market served as the dependent variable. So please don't infer any of this. All of you are getting jobs, regardless of quant skills. But I do think you may have more skills. You may anything that you do to have more skills, quant, qualitative, whatever, helps, right? It always helps your vocation. More skills helps. So don't just think about quant here. Anyway, to maintain equivalency across fields, graduate students who did not apply for jobs still after completing postdoctoral or fellowship were not included, blah, blah, blah. Your task is to use maximum likelihood in the ordinal package in R with the CLM function to estimate 3 generalized linear models. These are ordered logistic regression models, each predicting the job offer binary outcome. The M0 is an empty model with no predictors. M1 is a conditional model that examines the effective number of publications, number of conference posters, and categorical level of quant training. That's effectively looking at those as main effects only. And M2 is a conditional model that examines the additional impact of the interaction between number of publications and level of quantitative training. So that's model 1 plus the interaction terms. Term or terms, we'll get there. And this last paragraph tells us where we want to center things. Because 0 is already meaningful, do not center the number of publications or the number of conference posters. You can still use the GLHT function. Hooray! In the multcomp package, for any contrast needed beyond what appears in the model's summary output, please note I have experienced errors in p-values using one or more comparisons in GLHT at a time. So this is it. You can use GLHT, but only sort of, kind of. And this is where I was like, as I was putting this homework together, I'm like, really? Really, where is this? So what I'm going to ask you to do, instead of forming one big, where you had if you remember the GLHT code from homework 1, homework 2, and you were someplace you could add all of your effects into one big vector, don't do that. Just do them one at a time, which takes a little bit more syntax, but that's how I coded it on the back end, and that means you'll get the answer I got. It doesn't mean that either of us got the right answer, and I don't know what that right answer happens to be, but it's just disturbing for me right now. And this is part of the reason where there's sort of surprises that come along in R as I start to do this. What I'm learning is I really want my own package to teach you from, because then at least I can keep it regular, right? Keep it all in the same spot. But anyway. The low quantitative training group is the reference group. In each comparison question, the group before the versus is the base for comparison, such that the blah, blah, blah. I try to help you down with that. Use a type 1 error rate of 0.05. In the results section, you're going to use the results to Model 2, even if Model 2 is not significantly better than Model 1, mainly because I want to help you interpret interactions more. Part of the point of the course. Okay, so questions on what I just read. I then am going to start the homework myself. I have this file in my downloads. I start R, close my project. R script. So what I'm going to do is create a blank R script, paste in the syntax from before, save it in the same data as same folder as my data, and then close RStudio and reopen it with double-clicking on that file. Remember that from the last time? That was to get that was my easy hack to get the directory to be right in RStudio. If you already know the syntax for it, good for you. You can use it that way. For those of you who don't want to deal with that, this is the way that works most generally. Cool? Okay. This model syntax, 4228367. I can put my ID number in. What's that? I believe that was your social security. Actually, that's the social security number of our department chair. No, that's right. Just kidding. No. Can't tell you what that is. That's the combination to my luggage. Sorry. Spaceballs? Anybody? There you go. At least someone got it. I haven't watched that movie in ages. I don't know that it's aged well, though. Has anyone watched Spaceballs recently? Yeah, that's how old I am. That's what I grew up with, like Mel Brooks and stuff. All right. I did a lot of the coding for you already, so let's just go through this. I am creating the dummy coded group variables in the way we want them. So you see a quant m and a quant h. So remember, we have this quantitative level variable. There's 3 levels to it, and we were told to keep the low level as the reference group. That means we need to make a code for medium and a code for high. And that's what this syntax right here does. This package we're using, which is ordinal, requires that the outcome variable be in the form of what's called a factor in R. And I remember I talked to you about what factors were in class, kind of impromptu in the middle of homework 2. The factor is R's coding for it. So if I were to go and show you what this data looks like down here, you'll see it looks like the data from before. This is our job, but I put job F as my factor. The only way that you get a sense just from looking at it that's a factor is the levels at the bottom, 0 and 1. So what R does when it creates a factor is it says, oh, there's certain categories. This variable may have numbers to it, but I'm going to categorize them into different levels for it. Also with that, the other way you can tell it's a factor, there's a function named class. Data 1 star job F will tell us it's a class factor. So that's about all you can do to tell it. Yes?
What should we do if we're getting the message that there's no package called for?
Probably download it.
Could you remind
Yep, no problem. At the top of the, no, sorry, no, I don't mean to, Maggie, I'm sorry to, I wasn't trying to remind you that. Just, if you see there's no package, it's a good thing. Try downloading it, and then it's this install packages, and in quotes put ordinal. Yes, Jacetta.
So I did the homework already, and I remember that when I did start it, I got that error too, and it was because one of the libraries that you use isn't at the top.
Oh.
It was already downloaded, but it wasn't being called. I don't remember which library it was, and I can't see because I'm blind.
Okay.
But
Psych? Am I using psych over here?
The ordinal, because I got through it and I did have to look.
Okay, I'm sorry. If I need psych too, I'm sorry. If you just copy this whole section of syntax that you see, and wherever you see ordinal in that, put psych. Like that. Does that work? Oh, you can't see it? Is that better? Sorry. Sorry, everybody. I'm running out of font here. There we go. That's right. So just take all copy from the library ordinal up to has package, and just paste it somewhere below where ordinal is. And then in the sections in that line of code where you see ordinal, just replace ordinal with lowercase p-s-y-c-h. And run that first, that's right. What that will do is check to see that you have the psych package already installed. If you don't, it'll download it from the internet for you and install it. If you do, and then after either one, either if you do or don't, it'll load the library for you. So remember, in our packages, 2 things have to happen. You have to have the files from the internet, but then you have to load them. Right? And that's what this syntax is going to do for you. How are we doing? Okay. Bless you. Okay. I'm going to go back to the factor line again. Any questions on factors in R? Basically, to use this package, you just have to tell your dependent variable as a factor. So you just take what your variable you're saving the data in. In this case, it's data 101 star job or $job. Put it in the factor function, and out comes the factor itself. I saved it as a brand new variable. Because invariably, the thing that frustrates me most about R, well, one of the things that's very frustrating about R is the functions that require factors won't make a factor for you often. And then there's a whole host of functions that don't require factors that get mad when you send a factor variable in. And so this is part of the problem is there's no uniform standard of quality control in the packages in R, so that's one of the negatives about it. So, everything okay? Cool. Look at that, I gave you model 0. I tried. I'm trying. If you're worried about your grade on this, don't, because I'm going to make sure that you get the points you need, all right? But I'm more worried about you understanding the concepts. Model 0, the way that CLM works is very much like LM, right? We just put a C in front of LM. We give it the formula we want. Job F is the factor variable. It has to be the dependent variable, or the variable that shows up before this tilde sign. The 1 following the tilde sign indicates that we just want to run an empty model with no predictors, but estimate an intercept. Sound good? So I did that. Let's take a look at the summary model here. All right. So what do we have down here? We have 500 observations. Knobs. We have the log likelihood of negative 319.17. For me, your data probably will be different. AIC, so log likelihood, this is your first chance to use maximum likelihood, where you get the likelihood values out of the computer. Log likelihood is sort of the peak of the log likelihood for the data when the intercept, or the threshold, was 0.68. And it told us it took 3 iterations to get through, but it converged. So there we have it. Questions on the model? Should we do some interpreting? Now here's the other thing. This is not unique to R, but this is unique to generalized models, is that how you phrase the model can change from person to person. So this model, for us, we don't have an intercept that shows up. We have a threshold. And thresholds drive me insane, because they're really -1 times an intercept. But depending on which package you use, sometimes you'll get a threshold, sometimes you'll get an intercept, and they're clearly, sometimes, and in both of those cases, they're clearly labeled. At least this person says threshold coefficients. But sometimes you'll get numbers, if you use a different package, that doesn't tell you if it's a threshold or an intercept. And that's the part that drives me just batty. So, what's that? It'll just give you a number. Like, or it might call it intercept, or it might call it, I mean, who knows? Or an M+, for instance. There's a package called M+, that costs a lot of money. And that's one of the reasons I use R for a lot I do. I don't want you to have to pay $400 or $500 for just a statistics package. And in M+, it labels it sort of like a threshold. What is it? The variable name and then $0 or $1. It doesn't even say. I guess it's under the threshold section. So I guess most of them tend to do it. Yes?
What does threshold mean in terms of concept?
It's sort of, if you hypothesize that your dependent variable y, let's see if I can draw this. Man, this iPad thing. Gotta figure out what I did wrong. Anyway, if you imagine, so let's imagine our data here. Y can either be a 0 or a 1, right? If we were to pretend that underneath y, there was this hidden variable that's continuous called y star, right? And it had a normal distribution, then the threshold, I'm just going to call that the Greek letter tau. Anything, if y star were greater than tau, right here, this would represent the case when y equals 1. And then everywhere below it would be when y equals 0. What we end up getting here, why that happens, what's happening here is basically we're pretending that there's this underlying variable, and we can sometimes call this the propensity to be a 1. In this case, it's the propensity to get a job. And if it gets above a certain value of threshold, it becomes a 1. It's a complicated concept that doesn't need to be there, because you don't need to have that to do what we're doing with it. So here's what I do when I have to go and use a package I'm not used to. For instance, I wasn't ready for CLM when I went here, but CLM looks like it will grow with you, whereas if I was going to use the package GLM, which comes with the base R, but it does not allow you to have categorical variables with more than 2 levels. CLM will. So if you have a 3-category outcome, you can use it with CLM. You can't use it with GLM. I dropped, by the way, I dropped this section of multivariate for the last 5 years. This is probably why I did. It's just frustrating. Not just for you, but for me. So let's go in this and talk about this threshold. Because we're working with the empty model, we know our estimate is going to be some type of transformation of the mean. So let's take a look at the mean. What is the mean of our outcome variable? If I do mean data, what was my data set called? Data 01, here we go. Mean data 01, and I'm just going to use job here. I can tell you that in my data, 0.336 proportion, the probability someone got a job is 33.6 in the data. I want to align my estimate with that. My estimate is on logits. So if I have a probability of 0.336, if I were to convert that to a logit, would it be above or below 0? Below 0, right? So I'm getting a sense that my threshold, the number that's coming out of it, is really 1 minus the intercept. So if we try that, if I took negative 0.68117, and I took e to that value, that number, divided by 1 plus e to that same number, I should get 0.336 back. So, funny story. If you're sitting in your chair right now thinking, gosh, there's a lot to remember, I'm never going to do this, here's my life. I'm recording the video for you. Like, here I am, professing, doing my job, recording a video, purporting to know what I'm talking about in my typical overconfident way of doing so. And, I mean, Siri calls me awesome, right? So therefore. And so I get to this section, and I start to interpret this, and I'm like, well, and the intercept, and you can tell it's the intercept because, and I did the mean, and it wasn't it. It was 1 minus that value. And I had to cut that recording off, furiously go through all of my notes that I tried to figure out what this was doing, figured out that I dropped a minus sign in my code from it, one little dash, and realized where I'm going with it. So my point is this. It's always good to start with an empty model here because it gives you something about your data back. It's really easy to go see, observe things, and it helps provide an anchoring, for me at least, of where the number is. Is there any question on how I transformed my logit to my probability? Everybody okay? Okay. So let's go back to the homework questions then. Are you following along? Yeah, is this helpful? Cool. Homework questions. Now I can zoom in. The proportion of respondents who got a job, 0.336. You can tell. Look at that. It even suggests it for me. My log likelihood, negative 319.17. Where did I find that? To find what I was doing, I need the summary right here. There's my summary. Log likelihood, negative 319.17, right? The fixed threshold in logits is next. And that's the number that comes directly out of the computer. Right? And after that, it wants the probability. If you can transform that fixed threshold from logits to probability. Right? How do you do that? I know you've just seen me do it. Do you remember? That's right. E save it up here. So e to whatever logit over 1 plus e to whatever logit. Now it wants just that value for the threshold, not the intercept. Yes, Judy.
Yeah. So when you enter the fixed threshold in logit, it's your estimate value, right?
That's right. This one right here.
Yeah.
And then logits, it should be 0.681. So when I convert this to a probability, we should see it is 0.6639 or 0.664. And that should work. Come on. Why does it not submit? There we go. You see that? Does that help? Okay. So remember, e to logit over 1 plus e to the logit. That's the magic unlock key to get from logit back to probability. We rarely have to go the other direction. We rarely have to take a probability and convert it to logit because the computer's already done that for us. It's usually logit to probability. Okay, questions? All right, let's see Model 1. I'm going to make the Model 1 syntax real quick. Anybody want to help? Nobody wants to volunteer? I need the effects of number of publications. So what? That would be n pubs. I need the main effect of the number of posters. And now then I need the effect of categorical level of quantitative training. What do I put in for quant training? The dummy codes, that's right. Quant M and quant H. Now I can't put in quant level because that is a variable that has 1, 2, and 3. And if I put it in, it doesn't treat each group as having a distinct level. It tries to do a linear regression with it, right? So we're trying to do it differently by group. So if I do that, I take a look at the output. Here we go. Ta-da! I have an analysis. Everybody with me? It's getting very quiet. I imagine you're probably working on this. If you have questions, please do ask them. There's no question that is too basic in my mind, so you don't have to worry about that. Yes, Ryan?
Really basic one. How do you get the mean for the job?
You take the original variable and use the mean function. Yes, because if you take the variable that is the factor, it gives you. So if you convert, so here's the thing. If you get this message down here, up where you created your factor, you probably overwrote the job variable. So if you just named, watch this. What this line of syntax is doing is taking your original data job variable stored as a 0 or 1, converting it to a factor, and then copying it to a variable that has the name after the $sign here, so job F. So if I put capital JOB here, it's going to do that same process. Take my original variable, convert it to a factor, put it in a new variable named JOB, which is the old variable, overwriting the data I read in. And then if I take the mean of job, it gives me that error. So that's where I get in the habit. This is that frustration I have with R. To fix that, you have to reload your data from the file. Right? So this is where, like in the data science training that I'm trying to give you, anything where you might overwrite something, just make a new copy of it. Right? It's a good habit to get into. Does that help you, Ryan?
Yeah.
Yes, you're welcome. And by the way, I did that when I was building the homework too. Okay, full disclosure. You can name it however you want. You can call it job with a lowercase and capital F. I ended up doing that. I don't know why I did that. It was probably a typo. But so long as it's different than the original variable name, to maintain the original variable is not a factor. In R, it is very easy to go from a numeric variable to a factor. It's less easier to go from factor to numeric variable. It can be done, it's just not always easy to do so. So I always think of the factor as this black hole, and that's why I haven't really emphasized teaching it to you too much. I sort of gave it to you as a, if you have a lot of categories in a variable and you don't want to code them all yourself, use the factor. It's a black hole. It drives me nuts. Hang in there. I'm telling you, despite all this, I like R. Despite of it. In spite of it. Despite of itself. Ugh. Okay. Maybe it's just because I like R because it makes this sound I make when I use it a lot. Ugh. Yeah. I'm not a violent person, but R does bring out a lot of grunts. Do you have any things that you do when you get R and you get mad at it? Cry? That could be I know talking to Lisa, my spouse, about that. That sounds like she claims that's a gender difference. Like that's not always the case because I have been so frustrated I've cried certainly before. But mine is usually just want to throw the computer against the wall. So don't do that, please. Unless you want to get rid of your computer. Or if you do that, make it like a video and put it on make it viral, Anyway. Okay, so let's go back. Questions on this? Other questions? Okay, log likelihood should be pretty self-evident. You get that from Model 1 output right here. If you use the summary statement, everybody following? How do you get a likelihood ratio test? ANOVA, that's right. Thank you, whomever said that. Appreciate that. This is one thing I do like about R. If you put both of the models in the ANOVA function, it gives you the likelihood ratio test. Ta-da, likelihood ratio test. That to me is awesome. Like you don't get that in like R, and in SAS you have to do like a macro to do it. Although I guess it gives you this type of thing for some packages give you for the empty model. So I think it's pretty good. Maybe you don't, but I do. I will note, if you try to use ANOVA by itself, did anyone do that? Just ANOVA with like one of the models? Where we used to see our ANOVA table? It won't work. Did you see that? And this is my point that I was telling you. The ANOVA tables don't exist anymore. They're gone. We are already away from ANOVA tables. And yet here's the thing that we have debates about in the quant world, like pedagogically. Should we focus on ANOVA table in the early stat classes? And my answer is no, 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 no. Because if you focus on it, what happens? Well, we can still get all of our inference out of the other means. That's what we need to be able to do. So, likelihood ratio test right here. Likelihood ratio test, where does that come from? -2 times the difference in the likelihoods, right? Or the log likelihoods, pardon me. So that -2 times the difference is 176.78. There are 4 degrees of freedom. And it always gets compared to a chi-square distribution. Or at least, pardon me, almost always. Leave a little bit of room in your head for that to be different, but don't worry about that for this class. I know, there's lots of conditions. Questions? So, in looking at this likelihood ratio test, which model is preferred? Model 1 is preferred. How do we read this? Okay, this is a p-value that comes from this. This is the test statistic. Here's degrees of freedom. Here's the p-value. So there's clearly a hypothesis test going on here. And it talks about the concept we got to in maximum likelihood of nested models. Right? Model 0 is nested within model 1 because if we put a 0 in the coefficients for all of my predictors over here, we would get back to model 0. So this hypothesis is testing each of the betas, the beta for publications, posters, quant M, and quant H, simultaneously, all being equal to 0, against the typical omnibus test that you would have, which is at least one of those is not equal to 0, right? Kind of the case that where that condition wouldn't be true. So the very literal way of saying that is all the betas are equal to 0 simultaneously. The other way of saying it is model 0 is the null hypothesis, model 1 is the alternative. Right? So when you get a small p-value, you are used to rejecting the null hypothesis. That still stays true. So we're rejecting model 0. And at least one of these beta coefficients is not equal to 0. How are we doing? Yes, Ryan.
The betas are which are slopes, but they depend on intercept, right?
If you make a predicted value, anything where you'd make the intercept become meaningful or need it to do the value, then yes. The betas themselves, you interpret them just like you would any other term. Let's interpret them, actually. Let's do that. What does this beta coefficient for number of publications it mean? Or better yet, let's start. We always start with the intercept, don't we? So we have threshold. What is intercept? -1 times threshold. So the intercept is -2.02. That is interpreted as the log odds of a person with 0 publications. Sorry, log odds of a probability of a job for a person with 0 publications, 0 posters, who's not in the quant medium group or the quant high group. So this is a person with low quantitative training. Right, so that's the same interpretation that we'd get in regression, right, what the intercept means. But what does -2.02 mean in probability? That's where we can form that. So the probability that someone is offered a job with no publications, no posters, and with low quantitative training is 0.11. That's what it's telling us. Again, infer nothing about your job prospects from this. This is a poor attempt at humor. Of course I'm going to say that. I teach quant. It's good for business. How are we doing? What's that? No.
So it's saying there's like 11.7% chance that the person will get a job based on
0 publications, low quantitative training, 0 posters. Okay.
It's just the beta.
Yeah, go ahead.
When it's just the beta, you can make a percentage. There's this much chance. But when you're comparing to,
yeah, if you're going to make a predicted value, you can do that. So what we just did was the intercept. We really defined a person. We said this is a person who is, and we named a variable for all of those. If we were to talk about, here, let me show you a difference in just a moment. Okay, get down there. What does the slope for number of publications represent? For every 1 unit increase, for every additional publication that you have, person has. That's right. For every additional publication a person has, the logit of job, probability of job goes up by 0.41. Right?
But then can you convert that 0.41 in the same way you just converted the other thing to a probability?
Not a probability without anchoring all the variables that we have. Right? The only way we can convert it to a probability is if we include the intercept and make that work. So let's imagine. Let's take a person with 1 publication. Okay? A person with 1 publication, their value, I'm just going to take this. Their predicted logit would be the intercept plus the beta weight, right? So yes, I'm making a predicted value for them, and it says that person's now has a probability of 0.16.
And then you can subtract the 11, the 0.117 from that one.
Not easily. That's where we can't do that. So watch this. Because, for instance, let's imagine this person has two publications. Compare that with a person with two publications, right? Now their probability, so the difference between the first 0 and 1 is what, a little about 0.05, right? The distance between 1 and 2 is now 0.07, right? So the distance, so if we're going to compare, we can't compare with respect to probability. I mean, we can, but it's not really what's happening with it. What we can do with this, though, if you really want to interpret the coefficient, what we can do is convert it to an odds. Odds is going to be constant across the entire range. So that means we are going to talk about the increase in odds of getting a job for each additional publication. So if we take E to the beta weight and hit enter, we find the odds. So this is telling us for every one additional publication, the odds the odds ratio increases by basically 1.5. So the odds go up a little bit more in a person's favor. And that's constant across the entire range of where predicted values might be. Yes?
Sorry, the coefficient of X for n pubs,
Mm-hmm.
is that like for every increase in how?
So just like you would in a regular regression analysis, for every one additional publication, the logit goes up by 0.41. So if you're used to regression where you said y, or the outcome goes up by this much, just replace y with logit of y.
And that means that equals the probability of getting a job.
It's the log odds of the probability of getting a job. Does that make sense? So you have this one more step to go. It's like a filter you have to put your interpretation through. Like in homework 1, it was the expected score for a person was, this. If we were to do that in a logit model, it would be the expected log odds of the score of a person, right? So it's that one extra interpretive step that you have to go through. But the way that we work with these models, we still formulate everything like we did in regression. Everything that you learned there, we just have to put them through the logit filter, if that's a term. Questions? Has anybody seen logistic regression before this? A few have, not many. Okay. It's tough, right? It's crazy. But you were okay at the end of the last homework? It seemed like most of you were. You could predict things like crazy from these really complicated interactions. You're still doing that. Remember that. Even if you only get to, it's the logit. Now, I don't know where to go from there, but just remember that. Get to the logit, and then we can go to probability. Okay? Let's try it again. Let's keep practicing. What does this coefficient for number of posters represent? For each additional poster a person has, the logit of the probability of getting a job increases by 0.057. So again, because this is positive, we can say that they have a better chance of getting a job. Now, it's not significant, so it's effectively 0. But anything that's a positive value of this slope means the probability is going up as the number of publications or posters going up, right? All right, now we get a group variable. What does quant M represent? People in the medium quant training group, on average, have a logit that is negative, that is 0.58 units less than people in the low quantitative training group, right? Relative to the reference group. Right? And it's also significantly different for me, at least, in my data. Does that make sense? Absolutely. People in the medium quantitative training group have a log odds that's 0.58 less than people in the low training group. So put into words, when one logit's less than the other, we know that the probabilities, one probability is less than the other, right? So a negative sign right here means people in the medium quant training group actually have less of a chance of getting a job than people in the low quantitative training group. That's crazy. But does that make sense? That negative slope there, do you want me to say that again? Anybody? Yep, cool. Once again, people in the medium quantitative training group have a logit that's 0.58 less than the low quantitative training group. And what we can say that means is that people in the medium quantitative training group have a smaller probability of getting a job than people in the low quantitative training group. Sort of a weird result that you wouldn't expect if I'm selling you quant stuff. Justin.
So how would you use this as kind of a reaction to increasing pressures to be conversant to both qualitative and quantitative methodology?
I'd probably go with that. Yeah, actually, I would want to put the interaction in first. What we're actually seeing here is likely a missing variable. Like we omitted a bias. It's a bias. Actually, no, I would go with that. Yeah, let's say that's a good interpretation. If people who have a few more classes in quantitative methods are getting a less of a chance of getting a job, it seems like you want specialists more than people who are conversant in mixed methods or qualitative in addition to quantitative. It's an interesting finding, if you found this. Where to find this. Who wants to take a shot at what the quant H slope or beta weight represents? You can even just go up to logit. That's okay. It's hard, I know. I hear crickets, I think. Oh, Sarah's going to. Thank you.
People in the high quantitative training group have a log odd of 1.6437 more than the low quantitative.
That's right. And it's significantly different from 0. And so the last thing you tack on means if you have high quantitative training, your probability of getting a job is higher than if somebody who has low quantitative training. Now, how much higher? Well, that probability depends on how many posters and publications that you have, right? So it's not as easy as saying that, but just overall, we can say you have a higher probability. Yeah. Once again, this 1.64 says, roughly 1.64 says that people in the high quant training group have a log odds of a probability of getting a job that's 1.64 units higher than those in the low quantitative training group. And because it's higher and because it's significantly different from 0, that means that people with quantitative training, high quantitative training, have a higher probability of getting a job than people with low quantitative training. And again, infer nothing from this example. This does not apply to you. And besides, look at which class you're in right now. You take this class, you're all getting jobs now. Because I am Mr. Overconfident. Actually, no, I probably you're going to do well. I mean, not just because of this class, because you care, right? In general, I hope this class helps you in some respects. If you get a job, when you get a job. Not if, pardon me. I saw the glare. No, you're getting a job. That's why you're here. Have you seen the unemployment rates for PhDs overall? It's very low. Like, generally speaking. Like, when we had the Great Recession, I was very worried about my job prospects and everything as well. Even with the terrible unemployment rate, PhD unemployment rate was something like 2 or 3%, right? It's still much better than any other like job category. So yes, you're building resiliency to turbulence and who knows what. But so sorry, do not take this job example seriously. Underemployed, yeah, that's also true. We have a lot of that, and we do a very bad job with people who have PhDs who are lecturers here on campus. There's lots of reasons that we are bad for this, but there are, generally speaking, more opportunities with higher degrees. So hopefully that's what you see too. Sorry, riff, tangent. Please do not be offended by this. This is like the quant guy telling you, yeah, learn quant, it's good for you, right? All right, so clearly you can see the source of this. How are we doing with interpretation? Yes, question.
How we would interpret the estimate for the first location?
Yes, absolutely. We would see this and we'd say for every additional, because it's a quantitative variable, it's not a group variable, for each additional publication a person has, the log odds of the probability of getting a job goes up 0.415. And then again, if we were to translate that into better understandable terms for people who aren't versed in these models, which is like the world, we would say, because it's a positive slope, we would say that that means that for each additional publication, you increase the probability of getting a job a person has. Right? Each additional publication increases that probability. Pardon me?
Is that for all persons?
Yes. All persons. What you can't say from the logit is how much more. Right? Because if you think of a person who has 85 publications versus a person who has 86, their probability of getting a job is 0.995 on one and 0.996 on the other, but it will always be slightly higher in probability because this coefficient is positive. Does that help a little bit? How are we doing? Okay, so you can't quantify exactly how much the probability changes, but you can say it's higher. Should we go to Model 2? I'm not going to go enter in my numbers for you, but I do want to go to Model 2, and then we can start doing some GLHT trauma. I say trauma because I just realized I have too many coefficients here, I think. Anyway, Model 2. What do I need to add to Model 1 to make Model 2 work? Interactions between publications and quantitative training. And so I'm going to add a space down here. What is how would that look? How many additional betas am I adding? 1, 2, 3? 2, right? It's n pubs times quant m plus n pubs times quant h. How are we doing? Okay. So let's run this. Now, I built this homework this time trying to mirror what we did with the first homework. So you remember all those interpretations and how we were able to compare different versions of groups and how the interaction worked? We're still going to do that with this homework. So we're still going to have to form effects that don't show up in the computer, but let's take a look at what the summary says. Here are my coefficients. What does the threshold, well, let's take the threshold and convert it to an intercept, shall we? The intercept is -1 times the threshold, so that would be the log odds of the probability of getting a job for someone with 0 publications, 0 posters, and who is in the low quantitative training group. Now, that's when quant M and quant H are both 0 as well. How are we doing? Sorry, I realize I'm not giving you breaks today. I keep meaning we're going to get there. I'm sorry. Yes. Model 2, yes. Right here. Actually, let me go back to my syntax page. Here you go. So it's number of publications, number of posters, quant M, quant H, number of publications times quant M, and number of publications times quant H. Questions on that? Okay. You want to take a 10-minute break? My apologies. I told you I'm not good at this anymore. 10 minutes, we'll come back about 3:40.